Okay, let's take a look at some examples of kinematics equations. And you might say, you know, this first one at least, this is a Regents question, okay? An object moving at 9 meters per second experiences an acceleration of negative 3 meters per second squared. Until it is brought to rest, how far does the object travel during this time? So my recommendation from last year was always to label the things you have. You can either write them out to the side. I prefer to just kind of label right above the number what it is. So we have an object moving at 9 meters per second. That seems like an initial speed, so I'm going to write v naught. It experiences an acceleration of negative 3 meters per second squared. Remember, acceleration is a vector. It can be negative. That's fine. So that's A. Until it is brought to rest. So that's v. And it's important that we realize that that final speed, if it's getting brought to rest, means that it's 0 meters per second. How far does the object travel during this time? So we can say that what we're really looking for is x, and we can assume, since it doesn't say otherwise, that x naught is 0 meters. Now what I would do, I've spent, basically I just read the question, I labeled the things that I know. Now I just need to pick an equation that has, at least for this very simple case, that has the variables that I need in here. I have both the initial and final speed. I have the acceleration. One thing it doesn't tell me about is the time, so I don't want an equation that has time in it. Basically, that means I should be using this one right here. So I'm going to write it down. V squared equals v naught squared plus 2a x minus x naught. Let's see if anything is 0. Let's see, it's brought to rest, which means the final speed is 0. So I'm going to cross that one off, so that's 0. Initial speed is 9 meters per second squared plus 2 times negative 3 meters per second squared. Oh, and x naught, that's 0 too, isn't it? We're going to assume that it starts from the origin. It doesn't say that it doesn't, so we might as well just assume that, make it easy on ourselves. We solve for x. Okay, so I have 9 squared, that's 81. 2 times negative 3 is 6, so I'm left with, if I bring that to the other side, negative 81 equals negative 6x. So I divide negative 81 by negative 6, and I get x equals 13.5 meters. Now, that's a Regents question. You could have solved that last year from Regents. Let's see something that might be a little bit harder. An object starts at rest. Okay, so that's v naught is 0 meters per second. At the origin, that's also important, x naught is 0 meters, and accelerates for 6 seconds. There's our time. At this time, at that t equals 6 seconds, the object is at 72 meters. What is the final velocity? So, interestingly here, look what we're not given. We are not given the acceleration, and that seems like it could be a problem because all 3 of these equations have the acceleration in them. So it's like, well, are we allowed to use any of them? And the answer is actually yes. Okay. What I can do, because I know that the initial speed is 0, or the initial speed is 0 and the initial position is 0, if I look at my first equation, that'll knock out these terms right here. I know the time and I know the position, therefore I can use this equation. X equals x naught plus v naught t plus 1/2 at squared. That's 0. That's 0. The final position is 72 meters. The acceleration is, well, what we're looking for, and the time is 6 seconds. Now, 6 squared is 36, times 1/2 is 18. I divide that 18 to the other side, so 72 divided by 18, I get 4. Now you might be saying, well, why did you just solve for the acceleration? That's not what you're looking for. Yes, that's true, but if I'm going to find the final velocity, then I really need to know, well, one of the ways I could do this is if I did know the acceleration, that opens it up so that I can use either one of these to find the final answer. And in this case, I'm going to use this equation now. Let's see, starts at rest, so that's 0. We're looking for v. The acceleration is 4 meters per second squared. The time is 6 seconds. Final speed must be 24 meters per second. 4 times 6 is 24. That's one way you could solve this problem. There are other ways. Okay? Another way to solve this would be to find the average speed over this time period. Let's see, it was 6 seconds, object moved 72 meters. So if I use the average speed definition, where average velocity, I should say, if I use the average velocity definition where it's your displacement, which in this case would be 72 meters, 72 minus 0 is 72, divided by 6, I get an average speed of 12. And if I look at this equation, if my average velocity, is 12, my initial velocity is 0, then the final velocity must be, if I multiply both sides by 2, twice of the average. Twice of 12 is 24. So there are multiple ways to do some of these problems, but notice that either way I tried to do it, I needed 2 equations to solve that, okay, of the equations you were given. Some problems will require you to use 2 different equations. Okay, let's get to the last example. A train screeches to a halt in 20 seconds. And we also know another piece of information from the screeches to a halt. To a halt, that means that the final velocity is 0 meters per second. Okay, so we know the final velocity, we know the time, over which time it travels 500 meters. Let's call that our final position. And we might as well say the initial position was 0. If A is assumed to have been constant, what was the train's initial velocity? So I like this equation, or I like this question because it makes you think about the equation that we just introduced, this one right up here. The average speed, or average velocity, of an object is simply the final velocity plus the initial velocity divided by 2. Now, I'm looking for the initial velocity. I know the final velocity is 0. Okay. Now, if only I knew the average velocity. Well, it turns out that there is another equation to use to solve for average velocity. The definition. Let's see, that would end up being 500 meters minus 0 meters over 20 seconds. Let's see, 500 divided by 20, I think is 25. Yep. So V, the average velocity, is 25 meters per second. So I have 25 meters per second equals V naught over 2. The final speed, or the initial speed, initial velocity, I'm sorry, I'm going to do that a lot. The initial velocity is 50 meters per second. Now, I'm not quite sure, but I think this question might have been just about impossible to do if we didn't have this equation right here. It would be very, very difficult, possibly impossible, I'm not exactly sure, if we just tried to use these 3. It wouldn't have worked, so we did need that other equation. So even though it's not on the reference tables, you should become familiar with that equation. Okay, so let's move on to proportionalities. I like to think of this as like a little shortcut, okay? Proportionalities, this is a tool, and you'll notice that I do this when I'm in class a lot to check things very quickly in my head when I don't have a calculator. Using proportionalities is a shortcut if you know enough about the physics and if you're confident enough with your math to make predictions about how things should change. Oh, my pen is blotting there. So these are shortcuts that you can use if, and only if, the acceleration is constant, which will be in most of our cases. So here's what I'm talking about. Let's say that V naught, the initial speed, or initial velocity, is 0 meters per second. What does this equation become? The Fiat equation from last year, V equals V naught plus AT. Well, if V naught is 0, then all we're left with is this, V equals A times T. And if you look at that, A is constant, which means that T and V change. As time goes on, the velocity will change because there's some acceleration. If you think about it, if the time happens to double, then the velocity should double. If the time triples, the velocity should triple. So if I make T 3 times as big, and I multiply by A, which is constant and isn't going to change, that means that the velocity should then be 3 times as big. So what we call this is we say that V is proportional, that's the proportional sign, to T. And the way I would explain this using words is I would say if T changes by a factor, I'm just going to call a factor B, okay? I just need to call it something. So does V. That's a direct relationship. Whatever factor T changes by, V will also change. And again, that's only in the case where we have an object that's moving at constant velocity and it started from rest, okay? And this can actually be done with the other 2 equations as well, although it's a little bit more complex. Let's look at another one. If V naught is again 0 meters per second, and this time the initial position is 0 meters, then what will this equation become? X equals x naught plus v naught t plus 1/2 at squared. Well, if x naught is 0 and v naught is also 0, then this simply becomes x equals 1/2 a times t squared. Again, what we're going to do here is we're going to look at this and see, okay, well, what are the constants here and what are the variables? 1/2 is a number. Number is a constant. A is a constant, okay, constant acceleration. What that tells us is that we have t squared times some constant equals x. What we would say is that x is therefore proportional not to t, but to t squared. And here's what that really means this time. If t changes by a factor of b, x changes by a factor of b squared. Now it seems a little weird, but you can prove this to yourself. You can prove this to yourself by thinking, you know, you can make up some test numbers. Sorry, I'm just going to move this over so hopefully you guys can see a little bit better. Okay, there we go. Should be able to see the whole thing now. Sorry, my stand here is not cooperating with me. And my video just fell. Well, this will be fun to talk about when you guys finally get back to school. Hey, Mr. Remember that time your video was terrible because it fell all over the place? Yes, yes I do. Trust me, I absolutely remember it. There, we're going to stick with that. Okay, sorry about that. So, x is proportional to t squared. If t changes by a factor of b, x changes by a factor of b squared, which means that x ends up changing more so than t did. And if you think about it, it kind of makes sense. Even though the t has the squared on it, let's say you doubled t, okay, then that doubling of t, when you square that doubling, what you end up with is an extra factor of 4, which means if t doubled, then x is going to get 4 times as big. If t tripled, if you triple this value of t, then x is going to become whatever 3 squared is, 9 times as big. If you don't believe me, try out the numbers, okay? Try these out. Make up a table, make up an acceleration, and then try out different times and figure out what the final position should be. You should see that a small-ish change in t will produce a very big change, or a bigger change, I should say, in x. That's how this works, okay? And it's a little counterintuitive because it looks like you would imagine like, oh, that's squared, so that should be bigger. That's not really how this is working, okay? Whatever the squared quantity is, it ends up increasing x by more, because what we're saying is if you change t, you're going to have an outsized change in x, or a bigger change in x. Let's do one more with the other equation. And let's say this time if v naught is 0 meters per second and x naught is also 0 meters, then how does this equation change? Okay, so that term's going to go away, that's going to go away. What we're left with is v squared equals 2ax. And we have the proportionality now, x is proportional to v squared. Okay, kind of makes sense. If x is proportional to t squared and x is proportional to v squared, that means that v squared would be proportional to t squared. Or, more simply, v is proportional to t. It all kind of makes sense. So what this means is if v changes by a factor of b, then x changes by a factor of b squared. So it's the same relationship as before. Okay, this one's probably the hardest one to see just because we're not really used to comparing position and velocity. We're used to comparing position and time, or velocity and time. Comparing velocity and position is a little bit harder to see, I think. But basically what this means is that as you change the velocity, okay, if the velocity were to increase by a certain factor, that's going to increase the distance traveled, or the final position, by a huge amount, by a much bigger amount, which kind of makes sense. If you're always moving faster, you should also be going a much farther, getting to a much bigger position than you would otherwise. So again, these are shortcuts, and the way I've kind of always thought about them is they're useful for making really quick judgments. Like if you say, okay, you have something that falls for 2 seconds and something that falls for 4 seconds. How do you compare their speeds? You think about the proportionality. V is proportional to t. If you double t, you should double v. So if one falls for twice as long, it should be falling twice as fast. Now what a lot of people will say is, well, if it falls for twice as long, twice as much time, it should have moved twice as far as well. But the proportionality shows that that's not the case. The proportionality shows that if you double the time of fall, the final position will be 4 times as far away. And that's not something a lot of people would assume automatically. That's something that we have to have the math for, and then we can see that, oh, hey, this is actually correct. And again, like I said, you can make up numbers and try this on your own. You will come to the exact same conclusions that I have during this video. Okay? So that's it for the basics of kinematics. We'll come back and talk about graphing in kinematics in just next time with our videos. Hope you've enjoyed this. Hope it's been a little bit informative. I apologize for dropping the camera at about the 12-minute mark, and I will see you later.